Good morning. I welcome you all to this session of fluid mechanics. So today we will be discussing the topic application of viscous flow through pipes. Now last class we have solved the Navier-Stokes equations of motions in parallel flows, where we have assumed one thing, that flow is laminar, and we have deduced the expression for velocity profile and the flow rate and the corresponding pressure drop. Now there are two kinds of flow in a viscous flow. One is a laminar flow, another is turbulent flow. So we will come across these laminar turbulent flow differences afterwards. But now just in a short you must know that when the fluid velocity exceeds some value for a given fluid under a given flow conditions, the flow becomes turbulent. So turbulent flow in short is that the flow becomes irregularly fluctuating with time. That flow becomes an irregular functions of time. Flow is never a steady one. So at any point the flow velocity becomes an irregular functions of time, and this variation of flow velocity with time is random. So therefore we cannot have a steady flow that way. And another thing is that if there is a one-dimensional flow, that means flow is taking place in one-dimensional. In a laminar flow, all the fluid particles moving in that direction. So streamlines are parallel to each other. So planes are gliding over each other. But in a turbulent flow, what happens? There is a fluctuating velocities with time, and moreover the cross component. Even if there is no bulk flow, there is a flow generated small. The value is very small. The flow velocity generated in orthogonal directions to that of the direction of flow. So these are the characteristic features of turbulent flow. The flow becomes irregularly fluctuating with time. But one thing you must know at this juncture, that these fluctuations are random, so that statistical description is possible. That means this variation may be brought by the laws of, may be brought down by the laws of probability. So that an average velocity is defined, a time average velocity in turbulent flow, which is steady if the main flow is steady, or this average flow velocity is in one direction only if the flow is one dimensional. But strictly speaking, the flow at any point has got a three-dimensional nature, and this is irregularly fluctuating with time. This is a turbulent flow. Usually all flows in nature are turbulent flow. So laminar flow occurs with extremely small velocity, extremely small values of velocity, which are not usually encountered in practical applications. So most important thing in turbulent flow for engineers is that due to the turbulent flow, the fluid friction, the interaction between the fluid to solid and layer to layer fluid friction is enhanced. That means it offers more resistance for a given flow, which if you again translate to a very hardware language, that means for a given flow rate through a duct, the pressure drop across a length of the duct is much more than that of a laminar flow. That means if you make an analytical solutions from the laminar flow, then you will get a less value that you encountered in practice if the flow is turbulent. So therefore there the solution is not very easy. Nowadays with the advent of computational fluid dynamics or the computational mathematics applied in fluid mechanics problems, we can solve the turbulent flow situations, but still at certain stage the theoretical solutions or the computational solutions or numerical solutions need some help from experiments. That means they require some empirical information. And you know nowadays the closure models which have been developed for solving the turbulent flow, known as turbulence model, they are based on the empirical constant. So therefore a turbulent flow solution is not very easy. So in this class we will discuss this type of applications in turbulent flow, where an engineer is mainly interested in knowing for a given flow through a pipe what will be the pressure drop over a given length. And if I know the pressure drop, I can find out what is the pumping power required to force the fluid through the pipe. Or if I know the flow rate, if I know the pumping power, I can find out what diameter of the pipe should be. So this type of practical problems of turbulent viscous flow through pipes are solved in a very routine manner and conventional manner, which is not fully theory, not fully experiment. It's a combination of theoretical analysis with experimental information, known as semi-empirical approach, and will be done in this class. So let us now see how we can do it. So first we recall again the friction factor concept. So now we know, first we start with for a flow through a pipe. Let us consider this section is dedicated to viscous flow through a pipe and a turbulent flow, viscous turbulent flow. This is the pipe. Now this is the axis of the pipe. We take a control volume. Now let us consider a control volume whose surfaces are coinciding with the pipe surfaces. Let us take the control volume like this. Now we see that what are the forces acting on it. One is the shear force. This is the tau W acting in the surface, the same direction, because this is the surface gliding with the cylinder surface, so control volume. So flow is taking place in this direction, so therefore shear stress in this direction, tau W, acting on this throughout the surface. So pressure is acting at this cross section, let P. Let this is the piezometric pressure. We consider the pressure, static pressure plus the equivalent pressure head due to the elevation head, that is the potential from a reference datum. Why we take it? Because in case of vertical pipe or a pipe inclined in a vertical plane, the difference between the pressure from one section to one section is the static pressure difference in energy, static pressure plus the change in the potential head, which takes care of the gravity forces into account. This type of analysis we have already made. So there is a loss in piezometric pressure, P star. Let this is the length of the control volume or the fluid element as you tell. So therefore this is the loss over the length L in the piezometric pressure. So this difference will be the difference in piezometric pressures, which is the difference in static pressure if the pipe is horizontal. Now simply if we make a force balance considering the inertia force to be 0, you know a parallel flow through a tube or a pipe, the inertia force is 0, we discussed it earlier. So if we make the force balance of this fluid element, that means the fluid element is in equilibrium with the pressure and shear forces, then we can write this. If we consider the cross sectional area as A, if we consider the perimeter, weighted perimeter is S. This is not for a pipe also, this is valid for any duct, so that weighted perimeter is S, then we can write this P star into A this side minus P star minus delta P star, very simple, into A. This is the net force in this direction due to pressure force, must be balanced the opposite direction force, that is tau W into the surface area, that means the perimeter, weighted perimeter times the L. L is the length, that is the surface area. So simply we get from here tau W is what? Tau W is delta P star. Any problem you just ask me, S into L. So this is the shear stress, where S into L is the surface area, weighted perimeter into the length, that is this total surface area, S into L, over which the shear stress acts. So this is all right. Now if we define a hydraulic diameter DH, how do we define the hydraulic diameter? We have defined a hydraulic diameter which is defined as 4 times the cross sectional area divided by weighted perimeter. So this is the general definition of hydraulic diameter in relation to flow through a duct, internal flow, 4A by S. So therefore we can write A by S as 1/4 DH. So therefore this becomes is equal to 1 by 4 DH. A by S is that DH by L into delta P star. So it is all right with respect to this. So we get an expression relating shear stress to pressure drop, piezometric pressure drop. That means which takes care of the change in the potential head in terms of the equivalent pressure. In case of a horizontal duct, it is the static pressure drop. So you see that shear stress is related to pressure drop, which can be found out very straightforward and simple application of force balance on a fluid element when the inertia force is 0. That means physically it is because of the shear stress there is a pressure drop. So there was no shear stress for an ideal fluid, there is no pressure drop from this section to this section. That means at all sections pressure remains same for an ideal fluid. You know the energy also remains same. There is no dissipation of energy. So therefore the shear stress is related to pressure drop by this expression. Now if we go one step forward and if we recall earlier class, we discussed that coefficient of skin friction or skin friction coefficient, CF, is defined as shear stress at the wall divided by the dynamic head, rho V square. That we define that for any type of fluid flow, whether it is an internal flow through a duct or an external flow past bodies, the skin friction coefficient, a parameter dimensionless, defined as the shear stress at the wall, that means at the solid and liquid, solid and fluid adjacent to solid and fluid So tau W divided by half rho V square, where this V is the reference velocity, which in case of internal flow or flow through ducts is the average flow velocity. So if I write this definition and put this value of tau W, it becomes 1 by 4 into dH by L into delta P star by half rho V square. Okay, this CF is known as, this way again I write, CF is equal to 1/4 dH by L, all dimensionless parameter, dH by L and delta P star divided by dynamic head, half rho V square. So this way I write, this CF is known as fanning friction factor. Fanning is the person, Fanning's friction factor. This CF derived from the basic definition of skin friction coefficient in terms of a piezometric pressure drop or static pressure drop, as you tell, in case of internal flow and the hydraulic diameter, is known as fanning friction factor. That means it is derived from the basic equation of skin friction coefficient in terms of the shear stress at the wall, but then it is expressed in terms of the pressure drop. Since we know the relationship between shear stress and pressure drop derived from the force balance of a fluid element, then final expression stands as skin friction coefficient in terms of the pressure drop and the hydraulic diameter, and this is the average flow velocity in case of an internal flow through a duct. This is the average flow velocity whose definition is that Q by cross-sectional area. So if cross-sectional area remains same in the direction of the flow, the average velocity remains same, because Q always remains same under steady condition. So if average area, cross-sectional area changes, the average velocity changes. So this is the definition of Fanning's friction coefficient. So Darcy defines the friction coefficient F, that is Darcy's friction coefficient. This is Darcy's friction coefficient, another person, friction coefficient, who define the friction coefficient F as, doing away with 1 by 4, he left this 1 by 4, simply he defined dH by L times the delta P star divided by half rho V square, which means that F is nothing but 4 CF. That means if you multiply 4 with the Darcy's Fanning friction coefficient, you get a friction coefficient F. F is dH by L delta P star half rho V square. So this is the definition of the Darcy's friction coefficient. This equation defines Fanning's friction factor. This equation defines Darcy's friction coefficient or friction factor, whatever you tell. Now this equation is actually represented in a different form, not F as this. If we write delta P star is F into L by dH into half rho V square, this equation becomes useful to the practical engineers. What they do, that if they can know the friction factor for a particular flow from some handbook, from some chart, or from some predetermined experimental values, knowing the geometry of the duct, they can find out what is the pressure drop for a given length L. Geometry means the hydraulic diameter is known if he knows the flow rate. That means if I know the flow rate, so I can find out what is the pressure drop. From flow rate, I can find out the velocity, average velocity, knowing the geometry of the duct, that means cross-sectional area. Then one can find out what is the pressure drop in the duct. And one can find out the corresponding power requirement. Power requirement is no simply delta P into Q. So this is the amount of fluid flow rate, and this is the pressure drop over a given length. So to force that fluid at this rate over a given length, this power is required. So I can know for a given flow rate through a given geometry of pipe, that means for a given length and given diameter, what is the pressure drop and what is the power required. Or other way, if we know the power or pressure drop, I can find out what should be the flow rate. So this equation is very important in the applications of pipe flow through or viscous flow through a pipe. Now for a circular tube or pipe, dH is the pipe diameter d, because 4 times cross-sectional area is pi d square by 4 divided by the weighted area. Pipe is flowing full, so pi d, so this d becomes d. So therefore this will be simply L by d. So now the problem boils down in knowing the values of the friction factor. Now friction factor, if I come to the friction factor values in pipes, now let us write the friction factors. That means now I will discuss the friction factor, you will understand this is the Darcy's friction factor in pipes. Definition is like this: delta P is equal to this friction factor times L by D, length to diameter ratio, times what is delta P is L by D into half rho V square dynamic, where V is the average velocity, where V is equal to Q by. So this has to be there always in front of your eyes. That means in front of you this definition, friction factor. Now this F. Now first of all, in laminar flow we have already deduced the value of A. From exact solution we have found out Cf is equal to 16 by Re, Reynolds number, where Re we have found out from the Hagen-Poiseuille solution in the class rho Vd by mu. If V is the average flow velocity in the direction of flow, that means in the axial direction of the pipe. So these combinations of the parameters, dimensionless, this becomes a dimensionless parameter, this typical combination rho Vd by mu, which is known as Reynolds number. We have seen that tau W, but spin friction coefficient by half rho V square, which is nothing but Cf, which is the fanning friction factor here, 16 by Re. So F is equal to 64 by Re. So it is a simple analytical relation we know. But in turbulent flow it is difficult to develop that relationship from theory, but nowadays we are doing it with the aid of computational fluid dynamics, and also experiments are being done to match it, and even the solutions of turbulent flow, as I have told earlier, depends upon the experimental information. So they are generated basically from experiments. Now first of all you have to know, in a pipe flow the flow becomes turbulent when this Reynolds number as defined by this exceeds the value of 2000. That means Reynolds number less than 2000, the flow is laminar. So this Reynolds number criteria for flow to change from laminar to turbulent depends on flow to flow. So this is the 2000 Reynolds number below which the flow becomes laminar, and above which the flow becomes turbulent. This depends, this is only in case of pipe flow. For different type of flow, the criteria for Reynolds number for flow changing from laminar to turbulent is different. That means the values are different. But Reynolds number is the number, dimensionless number, which serves as the criteria for laminar to turbulent flow. So considering water, even at the ambient condition, if you take its value rho and mu, you can find out to maintain a 2000 value or below 2000 value, to maintain a flow laminar, you require, even for a very small diameter, feasibly small diameter, in laboratory or in practice, what is the value of V. That means the extremely small value of flow velocity or extremely small value of D can only make the Reynolds number less than 2000. For all practical applications of moderately large value of D and moderately large value of V makes the flow Reynolds number beyond 2000, so that flow becomes turbulent. And the turbulent flow, the friction, the geometry of the value of the friction factor or the shear stress changes. The shear stress, that is the friction between layer to layer of the fluid and that between fluid to solid, is enhanced by the mixing in the turbulent flow. That I will discuss afterwards. So turbulent flow, the only thing you know, the flow resistance, which is due to the friction between the fluid layers or between the fluid to solid, is increased. That means the viscosity is apparently increased. That's why a term apparent viscosity or eddy viscosity comes in case of turbulent flow. So therefore the flow resistance is increased, so pressure drop is increased for a given flow in turbulent region. But there is not a single equation by which one can fit the pressure drop and flow rate relationship or skin friction coefficient F versus Reynolds number throughout the entire range of turbulent flow. That means when the flow becomes, Reynolds number becomes more than 2000, so a single formula will hold good. So in different ranges, different formula are applicable. So people like Stanton, Niku-Retze, you must know the name, Niku-Retze, they work on it, and finally Moody is the man who documented in a very nice way, in a figure form, all the values of F versus Re for our use, and which is of great use and of popular use till today, and is known as Moody's diagram, which I will show you now. This is the Moody's diagram. This is what it is the friction factor versus Reynolds number. Now another fact I must tell you, that it has been found that in laminar flow the friction factor from analytical solutions of Navier-Stokes equation is a function of Reynolds number only. But in turbulent flow, friction factor is a function of both Reynolds number and the roughness factor. This roughness factor. So usually in laminar flow the friction factor is a function of Reynolds number, and there is another type of pipe, that is smooth pipe, whose roughness is almost zero. So there the friction factor is a function of Reynolds number. But for all commercial pipe it has got roughness. Roughness is measured in commercial pipe by the size of the or height of the protrusions at the surface. You know there are several methods by which surface roughness is specified. So for all commercial pipes we know the surface roughness, or other way commercial pipes are specified by surface roughness. This is the linear dimension. This either is specified either by measurement of surface roughness or by comparing the flow rate and pressure drop data of a commercial pipe with those of a pipe where artificially the roughness is created by gluing sand grain of uniform height, so that this height, the measure of this height is the measure of the roughness. Actually a statistical average of the surface protrusion is the measure of the roughness of a commercial pipe. So for commercial pipe in turbulent flow region, friction factor is a function of roughness. But for any commercial pipe, if the flow region is or the flow regime is laminar, it is a function of only Reynolds number. So only in case of turbulent flow the surface roughness comes as an influencing variable in friction factor. The physical reason behind this is that in case of laminar flow the surface, the boundary layer is so high so that the surface protrusion cannot protrude over the boundary layer, because these things we have not come across so far. This does not make any contribution to the velocity gradient at the wall to change the shear stress. So therefore this is not so in case of laminar flow, but in turbulent flow the surface roughness is an influencing parameter in changing the friction factor. It becomes a function of both Reynolds number and surface roughness. So this now has been plotted nicely by Moody. This is known as Moody's diagram. Here the friction factor is the ordinate, and this is the Reynolds number. This is plotted in a log scale to cover a wide range, and this ordinate is the dimensionless surface roughness. That means surface roughness epsilon by the pipe diameter, epsilon by d, which is known as relative surface roughness. Relative surface roughness. So now in laminar flow this is the equation F is equal to 64 by Re. Because we know we have developed this from analytical solutions of Navier-Stokes equation, that is Hagen-Poiseuille equation, that F is 16 by Re, Cf is 16 by Re, so F is 64 by Re. So this is the laminar flow. There is a discontinuity from laminar to turbulent start, because as you come to this laminar turbulent flow analysis you will see, so just after the laminar flow immediately the turbulent flow doesn't occur. There is a transition zone through which the turbulent flow is set up. And within this transition zone everything is unpredictable. The flow oscillates from laminar to turbulent, turbulent to laminar, so everything is very uncertain. So there is an discontinuity in the curve. We will see now. This is for smooth pipe, this curve. This curve is for smooth pipe, this curve. So after that you see the curves are branching off from the smooth pipe curves with the increasing order of the roughness. So increasing order of the epsilon by d. Now one characteristic feature is that in turbulent flow for rough pipes, you see after some Reynolds number the curve becomes more or less parallel, which means the friction factor becomes independent of the flow rate. Now here friction factor is inversely function of, becomes independent of the Reynolds number. Now if you define the friction factor, you should not be confused. Friction factor is decreasing with Reynolds number does not mean the pressure drop decreases with the flow rate, because friction factor is defined as how? How do you define the friction factor? F is, please tell me the definition of friction factor. F is, how do you define F? Delta P d by L into delta P d by L, friction factor, half rho V square. So you see, when friction factor is inverse function, linear inverse function of Reynolds number, this means delta P is a single, that means linear function of V. As you know from the Hagen-Poiseuille solution, delta P is a linear function of V, so F becomes an inverse function of V. So that friction factor decreases inversely with V. Here friction factor becomes independent of Reynolds number, means friction factor becomes independent of the Reynolds number, this means independent of velocity, because Reynolds number, if you write here, Reynolds number is rho v d by mu. So for a particular pipe, Reynolds number, change in Reynolds number means change in v. That means pressure drop is proportional to v square. That means when these curves are parallel, which means these are not functions of the friction factor is not dependent on Reynolds number, means pressure drop is almost a function of v square. So v square cancel, so friction factor we get constant value. But before that, friction factor is an inverse function of Reynolds number. That means delta p is a function of v to the power 1 to 2, not equal to 2, so that this friction factor becomes an inverse function. So delta p always increases with the increase of v, but the power represents whether friction factor will be constant or will be decreasing. If the power is more than 2, it doesn't happen in fluid flow practice, then friction factor increases with the increase in Reynolds number. This doesn't happen so. This zone is known as rough zone. That means pipe is completely rough zone or fully turbulent zone, where the friction factor is independent of Reynolds number, pressure drop is proportional to v square. And this portion where from the smooth, the curve of different commercial pipes of different roughness branches off from the smooth pipe, these portions rather is known as the critical zone. These are not very important, critical zone. Now what is important from the point of view of solving problems or doing the industrial problems, that one should read the value of friction factor from this Moody's diagram. That means if I know the roughness factor for a commercial pipe, if I know what is the Reynolds number, I can find out the friction factor. This curve is hardly used because practical problems are associated with turbulent flow, not with the laminar flow. So this is in all the Moody's diagram. Okay. Now come to the practical situations. So with this background, with this knowledge in background, now I go one step forward, that what are the different types of problems that an hydraulic engineer faces. There are typically 3 types of problem. One is that the flow rate and pipe diameter are given, find pressure loss over a given length and the corresponding power. This first type of problem. This is very simple. The straightforward school level problem. That means flow rate and pipe diameter are given. That means you know the velocity. That means velocity is given and pipe diameter is given. Find the pressure loss over a given length, and when length is given, you have to find out the pressure drop over a given length. Straightforward application of this equation. When the velocity is given, I can find out the Reynolds number, rho v d by mu, because v is given, d is given. So for water as the working fluid will be given that properties, rheological properties, and I know Re. So F as a function of Re, if it is a smooth pipe, otherwise a function of epsilon, I know the value of F. Straightforward I can find out delta P and I can find out the corresponding power Q into delta P. This is the straightforward application of this. But the second and third kind of problem is difficult relatively. Why? Because second kind of problem, the head loss over a given length of pipe of known diameter is given. Head loss means this one. That means either you express in terms of delta P or you express in terms of head loss. That means delta P by rho g. That means sometimes we express this equation in terms of the pressure drop as it was derived first, or in terms of the head loss. Head loss means loss of pressure energy. That means in terms of the pressure head, that means delta P by rho g, that means v square by 2g. Then this part becomes velocity head. Here the dynamic head have rho v square, it is per unit mass, this is the velocity head. Okay, so head loss over a given length is given, that means length is given, head loss is given, that means delta P is given. Find the flow rate and power required, you have to find out V. Why it is difficult? Because when V is unknown, we do not know even F. Because to calculate F from Moody's diagram, to see the Moody's diagram, we require the Reynolds number. Even if we require epsilon, main variable is Reynolds number. Velocity is not known beforehand. So Reynolds number is not known. So there are 2 unknowns. We don't know F, we don't know V. Because F is a function of V in turn to Reynolds number. So this type of problem cannot be solved straightforward, but it is solved by iterative procedure. That means here what we do, we guess a friction factor first and then we find out the first iteration velocity from known values of delta H or delta P, any way you write the equation. Then this second, the iterative value of V is used to find out the Reynolds number and find out the F from the Moody's diagram. Then use this F in this equation and find the second iterative value of V, and then again find out at that V what is the second Reynolds friction factor, and see the convergence between these two. This way this is being iterated. I will show you an example. The third problem also is the similar type. The flow rate and the loss of head over a given length are known, find the diameter. That means this is known, flow rate is known means V is known, but diameter is unknown. That means in this equation diameter is unknown, and diameter is unknown means friction factor is unknown. Because friction factor to know, I have to know both flow rate or the average flow velocity and the diameter. So either if diameter is not known, flow rate is not known, then the becomes an iterative problem. So it has to be solved by iteration. But if the flow rate and diameter and length is known and you have to find out delta H or delta P, first class of problem, this is a straightforward applications. So these three typical classes of problem exist in pipe flow analysis, pipe flow problems. So now let us see through typical numerical examples. Class 1 category of problem which can be solved directly. Determine the loss of head in friction when water at 15 degrees Celsius flows through a 300 meter long galvanized steel pipe of 150 millimeter diameter of 0.05 meter seconds. Here you see the loss of head is given. That means delta H is given. Determine the loss of head. Loss of head has to be found out. What is given? Flow through a 300 millimeter long, that means the length is given, the diameter D is given, this is D, this is length is given, and this is Q is given, meter, that means the average velocity is given. So nu of water is given at 15 degrees Celsius. So rho and mu coupled together, we have got nu. Epsilon for galvanized steel is given, that means the roughness factor is given. So this problem is a straightforward application. Now first calculate, now what we have to find out, the loss of head and the pumping power. Also calculate the pumping power required to maintain the flow. So let us find out first the average flow velocity. It is Q by pi by 4 D square, the cross sectional area. D is 150 millimeter, 0.15 meter square. So this becomes 2.83 meter per second is V. So therefore we first immediately calculate Reynolds number. Since I know the diameter of the pipe, what is that? 150 millimeter, 0.15 meter. So Vd by nu. Rho Vd by mu. So that is equal to Vd by nu. So I get the Reynolds number. Now from Moody's diagram, with the relative roughness, here roughness is given, millimeter. So to read Moody's diagram, I have to find out the relative roughness. 0.001, I find out F as 0.02, straightforward. This cannot be found from the figures that I have shown because I have not drawn the numerical thing. So straight away you see the Moody's diagram, it is given in each and every book. You straight find out the value of F. So knowing this value of F, one can find out what is the loss of F and what is the power required. So F is 0.02. How can I find out then HF? So delta H is equal to what? You tell me F L by D V square by 2G. Alright. So 0.02. What is L? L is 300 meter. So 300 and D is 0.15 meter. L by D into V square. V is 2.83 whole square. 2 into 9.81. So you straightforward get delta H, and this delta H is what? 16.33 meter. Now power requirement is delta P into Q. Delta P is rho G times this, that means 10 to the power 3 into 9.81 into delta H. Delta H means delta P by rho G in terms of the head. So head loss means the pressure loss, delta P by rho G. So again rho G I multiply it with delta H, so delta P into Q. What is the value of Q? So far I recollect 0.05. So this gives what? In terms of kilowatt, it is 8 kilowatt. So this is the first category of problem. Now second category of problem, you see, the second category of problem is the problem where the head loss is not to be calculated. Head loss is given either flow rate or diameter, so that the friction factor is not known beforehand. For example, we see this problem. Oil of kinematic viscosity 10 to the power minus 5 meters per second square. This is the kinematic viscosity. Property is given. Flows at a steady rate through a cast iron pipe of 1000 millimeter diameter. I am happy. The diameter is given. And of 0.25 millimeter average surface roughness. Surface roughness is given. If the loss of head over a pipe length is 120 meter, is 5 meter, that means loss of head is 5 meter and pipe length is given. L given, delta H given, this is the viscosity mu given, this is the D given, and of 0.2 meter, that means this is the epsilon given, So what is not given? What is the flow rate? So I cannot find out directly. Why? Because here the same thing, that if I write this delta H is equal to FL by D V square by 2G, then delta H is given. To find out the flow rate, I have to find out the average velocity, because diameter is given. But how can I find out the average velocity? Because friction factor is not known. To know the friction factor, I require Reynolds number. Again, to know Reynolds number, I require the flow velocity. So when flow velocity is not given, I have told that if flow velocity and diameter is not given, then friction factor is not known beforehand. So we cannot straightforward use this once and get the solution, which is known as explicit method. That means once you use the equation straightforward and get the solution. That is the first category of problem. But here you cannot do it. So what do we do? An iterative solutions. How it is? First you calculate the surface roughness 0.0025. Average. This is the relative surface roughness. Now then what happened? You guess a value of a 0.026. Now you can ask me, sir, how can I make a guess? You can make any guess, but in the order of 0.02, 0.01, this is the order of the friction factor. But depending upon your guess, the number of iterative steps will depend. If you can make a correct guess, the number of iterations will be less. Usually what you do is that you should do that with this epsilon by D value, at a moderate Reynolds number, you search a value of F from Moody's diagram. Just an arbitrary moderate Reynolds number in the turbulent flow, for example 10,000. With this relative roughness, I guess a value which is 0.026. Now with this guess value, first trial I can straightforward use the delta H value and can find out 5 is equal to with this guess value. This V square. That means I can find out the value of V, and this value of V, first iterations will give V is equal to 1.773 meter per second. With this V I again try to find out the value of F, because F was taken as a guess value. Then I want to improve the value of F. How? With this first iteration guess, so iteration, number of iteration you write here. First iteration, I find the value of Reynolds number. That means rho V, first iterative value, D by mu. So that is Vd by mu. Vd by mu. Mu is given. So this becomes is equal to 1.773 10 to the power 4. So you get the value of the Reynolds number. With this Reynolds number and the average surface roughness, or the epsilon by D, the relative surface roughness 0.0025, you get a value of F as 0.0316. With this F, you then find out the updated values of V, next step values of V. That means again you use this F, F is equal to L by D. What is L? F is equal to, sorry, not F, delta H is equal to 0.0316 into L by D, 120 by 0.10, same, into V square, the second iterative value, 2, divided by 2 into 9.81, which gives the second iterative value, second V square, oh sorry, how can I tell that first iterative value square is there, V2 square, 2 square, V2 square. So I get second iterative value V2, it is V2 square. So V2 is, second iterative value is 1.608. With this V2, I find the Reynolds number as 1.608 10 to the power 4. You calculate rho Vd by mu. Then with this Reynolds number, I see that my friction factor becomes 0.0. What is that value? That with this Reynolds number, I find 318. Now you see the difference between these two is very small. It is 0.63%. Where you will stop? In practice, you will stop where you see that your results are fairly accurate. You will have to take a judgment. If it is below 1%, the change in friction factor, we will definitely tell the convergence is achieved. That means we declare the final value of 1.608 meter per second. So you want to know flow rate? Okay, I can tell you. 1.608 into pi d square by 4. What is d square? What is d? 0.1. 0.1 square divided by 4. So this will be 0.013 meter cube per second. So you see, therefore, this category of problems where the diameter is not given, then we solve this category of problem where the flow rate is not given, or where the diameter is not given. That means to find out the diameter or find out the flow rate, we will have to make iterations. We first guess a friction factor, then find out either the velocity, average velocity, or the flow rate, same thing, or the diameter, and then the first iteration, then these values of diameter or the flow rate, whatever is to be found out. If one is to be found out, other is to be given. We update the Reynolds number, or we find the Reynolds number and update the value of friction factor. And then we compare it with the guess value. If we get exactly the guess value is given, that means your guess is perfectly correct and that is the answer. But if it is not so, then with that updated value of friction factor, you again calculate the diameter or velocity, which you have to calculate, either of the two. Then again you update the friction factor, and this way you see the convergence in the iterative procedure. But the first category where you have to find out the head loss or the pressure drop, there you don't have to do that, because there you have L, D, V, all are in your hand, beforehand to calculate. You straightforward use this equation once for all and get the value of delta P or delta H, and finally the pressure drop. So these three classes of problems are straightforward, faced in practice by an engineer, and they are solved like that. That means with the knowledge of friction factor, which is given or documented in a figure like Moody's diagram, or sometimes from a chart. That means you use a chart or Moody's diagram. This is full of experimental or empirical information, and then you use your theoretical equations developed from the force balance of a fluid element. That means the pressure drop connecting the length and diameter of the pipe and the average velocity, that is flow rate by area, through this friction factor, and you find out the parameters that you are going to determine. All right. So today up to this.